So, welcome to Environmental Geotechnics Ce488 interactive session number 18, and this is where I wish to cover another characterization scheme for geomaterials, which is what is known as the thermal properties of geomaterials. You must have noticed that since long we have been emphasizing on the thermal effects associated with the environmental fluxes, say heat or temperature, and how the systems or the materials are going to behave under these elevated temperatures. So, this is a topic of great interest to present day practice of civil engineers, mechanical engineers, environmental scientists, metallurgists, and for that matter for the entire society. I have cited several examples in the past that if you want to decompose the municipal solid waste, you have to maintain the right temperature in the landfills. All right. Now, I am going to give you a lot of different scenarios which might make you realize that why understanding the thermal properties of geomaterials is important. In other words, how materials are going to behave when they are exposed to thermal effects, thermal loadings. So, the question is that what are the real life situations where this type of discussion becomes important. I have listed some of them over here, which gives you a spectrum of what is happening in the real life or the field. The first one is, which we have been discussing since long, atomic waste disposal. You have been exposed to how atomic waste disposal units are disposed of in the geo-environment and how they are isolated from the geo-environment. We have discussed about the disposal systems, particularly the barriers, where we have talked about sand bentonite barriers. By virtue of this waste having or exhibiting very high temperatures, approximately 200 plus degrees centigrade, the geomaterial remains continuously in touch with or remains exposed to high temperatures. And this is where we have to ascertain whether this temperature is conducive enough for the geomaterial to survive, to sustain itself. In the previous discussion, when we were talking about the chemical characterization, we talked about TGA, DTA and DSC, differential scanning calorimetry, thermogravimetric analysis and differential thermal analysis. These are the three techniques which are used. We call them as TGA, DTA and DSC. Thermogravimetric analysis, then differential thermal analysis and differential scanning calorimetry. So, this tells or this indicates that how much the material is vulnerable to elevated temperatures. Now, when we talk about vulnerability, vulnerability is an adjective. How will you quantify it? The best way to quantify this is weight loss because of very high temperatures. So, if a material loses enough weight when it is heated, it is understood that this is vulnerable to high temperatures. All right. So, if you look at the pattern of the TGA, what it shows is that weight loss as a function of time. Now, this weight loss could be because of expulsion of water, which is hygroscopic in nature. This weight loss could be because of the expulsion of the volatile organic compounds which are present in the soils, contaminated soils. So, the question is that how will you estimate that the soils are contaminated or not? Take the soil samples, expose them to high temperature, slow rate of heating in TGA, DTA, and then establish what is the weight loss. Concrete technologists and the material scientists who are creating new materials use these techniques quite a lot. All right, because what you require is a stable material or a compound in terms of the chemistry. So, these type of studies can be done. Now, coming back to the nuclear waste disposal, you remember some time back I discussed that the need of the hour is to create synthetic minerals which can sustain high temperatures, because most of the time earlier people used to mine out the minerals which were good enough to sustain thermal loading. But now the days are different. Mining is a question mark because of several issues. I think we have discussed about the impact of mining, social, where to displace people, all right. The place where you are doing mining is already gone, where you are dumping the dumps of mine, that is also gone. Nobody wants to lose his or her own native place. How will you displace the population is a big question. So, imagine these type of things are going to become much more trivial in the days to come. So, we were discussing about creation of minerals. Now, these minerals should be withstanding the thermal flux. Got it? Again, this is English. The question is, how will you quantify this? That a material can sustain thermal effects. We will discuss about this. What are the parameters? What are the properties which can be obtained to make sure that the material is not vulnerable to thermal loading and it can sustain this thermal loading. So, radioactive waste disposal requires lot of studies related to thermal properties of geomaterials. The next in the series is any industrialization which takes place requires transmission of power, electricity. So, this is where high voltage underground power cables which are being installed to operate industries is a very big question. I am sure you must be wondering that why civil engineers or geotechnical engineers or environmental geotechnologists are required to study these things, because the power electronics guys need this feedback from you. I did lot of testing for cable manufacturing units in the country and abroad. Why? Because the cable rating defines up to what amperage this cable is going to sustain the temperatures which are getting generated in the porous media or the soil mass on the rocks, when current is passed through it. Very interesting topic to study. I hope you can realize that unless cabling is done, high voltage of the current is passed through, industrialization cannot occur. So, this is where actually our subject interfaces with the guys who design cable systems. We will be discussing about this later. The next one comes road pipeline structures in the cold regions. Those of you who have visited the cold regions must have realized that permafrost is a major problem. All right. Now, if you want to industrialize these locations, right now Government of India's emphasis is much more on the northern part of the country, where most of the time the soil mass remains frozen, all right, and when it thaws, when it melts, again the structure of the soil mass changes. So, those of you who might get a chance to work in this field of permafrost engineering or the cold region geomechanics would definitely like to work on the thermal properties of geomaterials. Most of my students who are working on very advanced topics like CCUS and all, I hope you can realize when we talk about the multi-phase creation of the soil mass or the rock mass or a geomaterial, I can impose the geomaterial which is in the fully saturated state to thermal gradients, and I can create a partially saturated state of the material, all right, and then I can study the properties. So, these type of infrastructures which are located in extremely difficult climatic conditions, both ways, either there the temperatures are very high or the temperatures are very low. So, just now I gave you an example of the permafrost. The second extreme is going to be deserts through which the cross country pipelines which are carrying crude oil or which are carrying water are passing through. I hope you can realize that the temperatures outside are 55 degree, 56 degree temperature. I hope you can realize, you can relate it to the real life situation where the cross country pipelines are passing through deserts. Now, how will you insulate these pipelines is a very big question. Alright. So, this is another extreme situation which I have created. So, both the temperatures in the negative region or the positive regions, extremely high temperatures are going to become a big problem for you. In cold regions, the big problem was freezing and thawing. What about the regions which are arid, where the temperatures are extremely high, and if you are passing a fluid through that, I hope your concepts of fluid mechanics will alert you that there should not be any cavitation which is going to take place in the pipelines. So, I am sure you must be realizing that mechanical engineering, process engineering, civil engineering, geotechnical engineering, environmental geotechnology, these are all interrelated. So, if you are executing a project where you want to convey a fluid under extremely hot climatic condition, you have to make sure that cavitation does not take place. And to avoid cavitation, what you have to do? You have to insulate the pipelines. Sometimes these pipelines are above the ground, which is not very safe. Why? Social issues. I hope you understand that why I am saying social issues without going much into the details. So, roads, pipelines, infrastructure which is being done in the extreme climatic conditions requires understanding of thermal properties of geomaterials. Similarly, I am sure you must have heard about the agriculture and aquaculture fields, the solar ponds, agriculture related issues. Why it is required to study the thermal properties of the geomaterials? Because for aquaculture you require a particular temperature. Similarly, for agriculture also submarine condition, algae is a beautiful example where you need to maintain the temperature of the ponds. Similarly, solar ponds also require this type of understanding of geomaterials. So, most of the time what they do is they make the ponds which are slightly below the surface, about maximum 5 to 10 meters deep. Now, the major challenge here is if you are doing aquaculture, you require agriculture also to be done under subwater conditions, so that becomes the feed for the aquaculture, for the fish, for the prawns, for all sorts of varieties of species of prawns and shrimps and whatever. So, unless the temperature is maintained, you cannot execute these projects. That means all these ponds should act as a best possible sink of heat, and they should not allow heat to go out of the control volume. Got it? So, this is the issue. Now, you can do the modeling for such type of a situation. You can create a control volume and you can see how the heat losses might occur from the foundations of the ponds, not because of the evaporation and transpiration. This is an interesting topic which people are trying to pursue. Ground improvement techniques. I have been talking about a lot about heating and freezing to be adopted for improvement of the ground conditions. I think if you follow what is happening in the recent times, the tunneling is a process which, if done in highly pervious soils like sands, there you have to freeze the entire soil mass to make it monolith and then do the tunneling operation. Otherwise, the water seepage will become a very big problem. So, ground improvement techniques, heating has been done. Similarly, freezing has been done to execute the projects. Most of the time, yes please. Suppose this is a ground. Have you heard this story that during Second World War, how did they make landing pads for the small aircrafts overnight. So, this is the marshy land. Okay. Now, suppose if I heat it from the top, what will happen? The way you make bricks, I can make a hard strata. This is what is known as a heated soil mass. This is what a sort of a desiccation is. What nature does to the marshy lands. So, top few hundreds of meters or centimeters of the soil mass gets desiccated. So, this varies from, let us say, few centimeters, 100 mm to approximately 600 mm. I am just giving a a rough picture. So, this is the heat treatment, okay, over the marshy land, and now you can land the small aircrafts. Army people use these techniques quite a lot. What I can do is I can have a heater mounted truck, and through that I can emit the hot gas or hot air, and that will also give me the same effect, just like baking the cake. So, you take the dough, put it in the oven, what happens? Both top and bottom become stiff, in between there is a soft deposit or soft material. So, this is a good example of how heat induced stabilization can be done for soft clays. I think this is what you are asking. Another thing you must have heard of, I am not sure, there are some PVDs, prefabricated vertical drains. I think I taught you in this third year course, consolidation, 3-dimensional consolidation. So, these PVDs are the prefabricated vertical drains which are used to stabilize the clays or the marshy lands. If I club it with heating device, so now what is happening? This is a thermo-hydro-mechanical coupling. So, in this PVDs, I will include a heater assembly also, and what this heater assembly will do? This will heat also the soil mass, and hence you can stabilize the soil. Clear? So, this is a beautiful example of thermo-hydro-mechanical coupling. Now, coming back to the granular materials, suppose if I want to do tunneling and this happens to be sands and I want to make a tunnel over here. So, the permeability is very high of sands. What I have to do is I have to isolate this much portion of the soil mass and freeze it. Now, what this freezing is going to do? This freezing is going to convert sands to a monolith system like rock, which are impervious. So, from a pervious system, you have converted the material to a impervious material. I hope you are realizing that how you can play with the situation and the material to get the advantage. Fine. So, this is the question which you are asking, and then once it has been converted into monolith, I can cut it out using a TBM, tunnel boring machine. Got it? Only thing you have to do is you have to maintain the whole soil mass under frozen conditions. So, you have converted from a very granular pervious system to an impervious system. These are the two examples. Anything else which comes to your mind? Yes? It has been achieved. There are few cases. If you check on the net, and you will find that there are few projects which have been done like this. But then at what cost is a major question. So, cost is going to be extremely high. But then when you want to execute a project, as I said, cost should not be a deterrent, because what is more important? You are making all these tunnels at what cost? But in the long run, if you do a LCA, life cycle analysis of making a tunnel, you will realize that you are going to save so much of carbon emissions, so much of environmental impacts. So, cost is a misnomer. You have to perform an LCA analysis to see whether this cost is justified or not. And this is where your role becomes important as a civil engineer. Clear? Because LCA reflects the economics part also, but that economics also deals with the environmental impact also. Yes.
Instead of doing this, can we punch like circular sheet by like hollow structures like inside, and maybe then.
So, check out on the net. I think I had shared some videos with you how sheet piling is done. Please remember one thing, anything which you drill in the lateral direction is known as horizontal drilling, is very, very difficult. This is what is known as trenchless technology. Read more about it. I did this at one of the airports in the country on an active runway. Trenchless technology. Okay? This is what is known as horizontal directional drilling, HDD, correct? So, the sizes are limited. So, then you require a tunnel boring machine to make a big tunnel. Otherwise, mostly this is used for small utilities if you want to lay them up to 300 mm, not more than that, 30 centimeter, correct? So, sheet piling is not a solution, very difficult to insert something in the lateral direction. Fine? Okay. Any other question? So, I think I have answered a lot of questions related to what we have been discussing. Okay, let us move ahead. Yes, anything else? Fine. So, ground improvement techniques by using soil heating and freezing. This could also be by purging hot air. So, this is also a heating process. Normally, hot air purging is used to get rid of VOCs from the soils, volatile organic carbons. Okay? This is also a sort of a remediation technique. I am sure you must be realizing that each one of these situations and statements is an entrepreneur's job. So, you have to pick up one topic out of so many and become a practitioner, become an entrepreneur, chase it, and you will be the only one who will be doing all these things. So, dream like this. Energy conservation schemes. I have already given an example of how energy storage ponds are being created. All right. Today's world is all about energy storage. So, please try to study how underground space is being utilized for energy storage. All right, particularly hydrogen. Everybody is talking about creating hydrogen, but where are you going to store it? You can't store it in containers. So, they have to come back to geotechnical engineers. Are you realizing the importance of our subject? So, this is underground energy storage, which requires creation of different types of storing facilities. So, the moment you go underground, it's all about our subject. Any other example which comes to your mind? Anybody's? Energy storage? Crude oil caverns, yes. Underground space energy storage could be hydrogen, it could be caverns for oil storage. See how subject develops. Look at what's happening in the society. Do we have faith on each other? How these sabotages are being done. So, nothing is nowadays being thought of above the ground. Why? Because we do not have confidence in our own people. I gave you one example. Most of the oil line and water pipelines are underground. Why? To stop sabotage. Clear? So, gone are the days when everybody used to create overhead or overground storage facilities. Now they are using the underground space for storing energy. You are right. So, storing the oil, hydrocarbons, water, sorry? Yes, why not? So, atomic shelters. So, most of the gases and the chemicals are transmitted underground. I mean, you join any industry for that matter, I am sure you will come across designing such type of systems. Heat losses from the basement of the buildings. This is also a very big issue. You have the buildings and many times you create a warehouse by putting a base slab. And then this building is going to be air conditioned. Most of the losses occur from the base of these warehouses and storages. Any other example which comes to your mind? Some time back we were discussing about foundations for oil tanks. You remember? So, this is the oil tank and I was talking about cavitation effect for the buried pipelines. Now, what is going to happen here? If the soil mass is not a good insulator, during summer times what will happen? There will be an exchange of heat from the contained fluid to the ground and from ground to the contained fluid, again a problem. So, most of the oil companies are having this problem of designing the foundations where the changes in the climatic temperatures are too much. Very simple things, but then the answers are not available. I hope you are realizing that foundation engineering course you must be doing, correct? So, what we are doing now, we are going beyond the bearing capacity and settlements. We are talking about how to make the facilities useful for or worthy enough of storing the facilities which you are creating. Warehouse can be used for storing different type of materials, goods, vegetables, grains and so on, and these facilities are used for storing the export, import, oil, different types of chemicals and so on. Then comes the energy geotechnics, the topic which is very close to our heart and we are expanding too much into it these days. So, what we have discussed there about the energy storage is also a part of energy geotechnics, particularly the multi-phase geomechanics. Okay. So, most of the examples which we have discussed so far, my students have talked about gas hydrates, geothermal energy, enhanced oil recovery, carbon capture utilization and soil freezing characteristic curve, I think we were discussing about it, heating and cooling front migration and the moisture vapor phase creation, transport of contaminants and all, everything comes under this category. So, the canvas is quite vast, you must be realizing. Unfortunately, we have never discussed formally the thermal properties of geomaterials. Nowhere in conventional geotechnical engineering, we talk about thermal characterization of geomaterials. So, these are the situations where thermal characterization becomes very, very important. All right. Now, what are the thermal properties? Let us spend some time on this. So, thermal properties are three. The most relevant ones are thermal resistivity, then comes thermal conductivity, diffusivity. Thermal conductivity is the inverse of resistivity, and of course, the specific heat. In your basic physics courses, you have studied all these things. What are resistivities, what are the diffusivities, what is the specific heat. So, these are the 3-4 terms which we need to understand the thermal properties of the geomaterials. I am sure you must have used the term thermal inertia also of a material. Insulators will have very high thermal inertia. Can soils be insulators? Yes. Whether this characteristic of the soil to insulate migration of heat is good for a structure or not is a big question. So, let us explain or let us discuss a bit more on, suppose if I want to create a industry, all right, and I am doing cabling. This is a cable, electrical cable, all right. Now, electrical cable, once it is laid and it is charged, it is going to carry current I, and its resistance is going to be R. So, I am sure you must have studied that total heat which is getting produced will be I square into R. Now, if this heat gets created because of charging of the cables, all right, and it is trying to dissipate out of the cable, but suppose if your soil happens to be a poor conductor of heat. Now, what will happen? If this happens to be a poor conductor of heat, what will happen? Very good. Cable will get heated up, and then what will happen? Very good. Resistance will increase. RT equal to R naught 1 plus alpha delta theta, correct? Now, what is going to happen? If resistance increases, I will decrease, and then ultimately there will be a stage. What will happen? If the temperature becomes very high, what will happen beyond that? The whole cable might get burnt. I hope now you are realizing what is the importance of the soils and when you are dealing with the cabling operations. Now, without cabling, industrialization cannot be achieved. So, what we have done is very conceptually, we have discussed that why it is important to understand the thermal properties of the geomaterials. Now, you can superimpose the conditions, boundary conditions. This could be dry soil mass, this could be wet soil mass, this could be variably saturated soil mass, there could be a water table on the surface, there could be a partial saturation, partial submergence, it could be sands, it could be clays, it could be rock mass and so on. Depends what is your objective, what is that you are trying to create over here. Is this part clear? So, the 3 properties which we have talked about are thermal resistivity, and the inverse of this is thermal conductivity, then diffusivity and specific heat. So, the whole story is about getting these 3 parameters, how we can obtain these 3 parameters. When I started working on this topic, unfortunately there was no tools available in the market. So, what we did is we created our own tools for measuring thermal properties. This was long back in late 90s when we started working on this topic. So, this is the relationship which relates all the properties of the material along with its density. Okay. So, out of these 4, at least you should be knowing 3 parameters, and then you can obtain the 4th one. So, this becomes a chicken egg story. Which parameter should be obtained, how to get the other parameter which are not known. But interestingly, I hope you can realize that the fingerprint properties of the geomaterial would be Cp and RT. So, that means if I have to create a classification scheme based on thermal properties of the geomaterials, I should be knowing its specific heat and its RT. Specific heat you can obtain by DSC. differential scanning calorimetry also, which is what most of the chemical engineers use. The problem is in DSC you have to use a very small sample, few grams or milligrams, not more than that. So, it is not fit for civil engineering applications. All right. So, what we have to do is we have to devise a technique by which we can compute Cp also. So, I will discuss about this. Measurement of RT and alpha is straightforward, and the moment you get RT, inverse of that is going to be conductivity. So, most of the cabling companies, what they need is they need thermal resistivity of the soils. So, this simple concept I utilized to do several consulting projects, and there was a time when we were exporting our creation because the world was not having a simple tool to measure thermal properties of soil, which my students created. I will take you through all those type of creative work in the time to come. Interestingly, this is nothing but the heat migration through the geomaterials, correct? So, this is what is heat migration. Okay. Now, this can also be extended to migration of fluids like water, they are equivalent. Now, when we talk about migration of water and fluid, the hydraulic conductivity K, let me put it as Kh, which you might have studied, can also be utilized. So, heat migration through a geomaterial can also give an idea about the migration of water or the fluid through the geomaterials. This is what is known as equivalence. Some time back, we were discussing about the soil water characteristic curve. Okay? That means, I can utilize these properties also to create SWCC or SFCC. Now, if you get a chance to work in environmental geomechanics, you have to deal with SWCC and SFCC definitely. We were talking about some time back the two extreme climatic conditions, one in deserts where the temperatures are very high, clear. So, water retention capacity is important. So, this is for elevated temperatures. And this is soil freezing characteristic curve, this is for sub-zero temperatures. I hope now you can realize that how the modern day geomechanics is dealing with environmental effects. Let me remind you, soil water characteristic curve is the characteristic curve of the soil, how easily or how effectively it can lose moisture through it, where suction plays an important role, soil suction. So, soil suction is nothing but a function of the temperature. When soil mass is getting dried up, suction builds up. So, this is nothing but the suction property. SFCC is also a suction, but then this suction is because of freezing of the water. Look at the two things. One, you are losing moisture from the soil mass when it is being heated up, evaporation, clear, vapor formation. The second one is I can lose the moisture from the soil mass if I freeze it, depends upon the type of application which you are into. So, the first step towards studying all these hi-fi things which we are discussing under CCUS, gas hydrates, energy storage would be to quantify SFCC and SWCC. The moment you have done these two, you know how the soil mass is going to behave under different temperatures. And you can predict all the properties, geomechanical characteristics, once these two curves are known. So, this will give you an idea about the geomechanical response of the geomaterials, geomechanical response of the geomaterials. Hope you have realized this concept. Okay. Any questions? So, this is a slightly intricate subject, but I wish that some of you at least will like to take it up as a your professional job or maybe professional activity in the days to come. Master this. Now, when we talk about all these processes, there are several factors which are responsible for the response, correct? Any property which you measure is bound to get affected by several parameters. What are those parameters? I have listed them here. The first one is type of the geomaterial. You must have realized that I bifurcated this discussion between a granular material and the clays. Okay? So, type of material is very important, and the third thing could be composition of the two. You have sands, you have clays, and mixture of the two, and how the properties are going to change. So, these properties are going to be a function of type of the geomaterial. When you say type of the geomaterial, particle size becomes important, specific gravity becomes important, its constituents become important. Why? Because each mineral has its own fingerprint, thermal response. Got it? All right. So, how heat is going to migrate through a mineral composition is dependent upon its ease of migration of heat or the flux, that is RT, and how much heat it can store. So, in this case where we were talking about the cabling procedure, if soil mass would not dissipate heat very quickly, then what will happen? The temperature will build up here, and then ultimately the ampacity of the cable might decrease, and there might be a situation where the entire cable may lose its integrity. Fine. So, I hope now you are realizing that how to simulate these simple effects mathematically and then do mathematical modeling. So, the type of geomaterial is important, moisture content is very important, because heat migration might occur through grain to grain or from grain to pore fluids or through pore fluids only. Three mechanisms: grain to grain, provided the contacts are good, a dense soil mass where grain to grain contact is very good. So, heat will migrate from one grain boundary to another grain boundary. Loosely compacted soil mass, dry or saturated. Once the water comes in, what is going to happen? You have some medium through which the heat will migrate, and water is less resistive for heat as compared to the air. Air is a better insulator than water. I hope now you are realizing that how saturation of the soil mass or the geomaterials or the rock mass is going to play an important role as far as the heat migration through is concerned. So, I am just giving you the basic concepts here. Is this right? And then what you have to do is just utilize these concepts to model the type of problems which you are dealing with. Then comes the distribution of the grain size. Why? You have been studying in third year soil mechanics that what is the difference between a poorly graded soils and uniformly graded soils? Density. So, if you are working on materials which are poorly graded, you cannot compact them. If you cannot compact them, their heat carrying response is going to be different than the soil mass where the compaction densities are very high. So, this is where the particle size distribution becomes very important. So, particle size distribution actually influences these parameters directly or indirectly. For that matter, let us say clay fraction. If the clay fraction is too much, what is going to happen to the resistivity? It is understood that the clays are going to be more resistive than the granular material, but the story may change depending upon the moisture content. So, what water is going to do? The water is going to expel air from the pores, and then it might make soil more thermally insulated or thermally conducting, depends upon what type of condition you want to create for your project. Fine. Density of the geomaterial, more the density, better the contacts, better the heat conduction. temperature and pressure. So, just now you were talking about the resistivity is a phenomena which depends upon the temperature and of course, the pressure. Okay. Pressure is less understood so far. However, the temperature part can be studied. I can expose geomaterials to different pressures and temperatures and see how the thermal properties are going to change. Presence of contaminants, how the contaminants are going to change the thermal response of the geomaterials. So, suppose if you freeze the soil mass, the crystal of the ice which are getting generated in the soil mass would act as a contaminant. Why? Because they were not required there, suddenly they got created. Gas hydrates, which we have been talking about, gas getting trapped in the pores of the soil mass and under sub-zero temperature or near zero temperature, they might get frozen. The thermal response of the geomaterial is going to change. So, most of the guys who are working in the field of gas hydrates, carbon capture utilization, they talk about thermal properties of geomaterials. Okay. In simple terms, presence of different type of salts in the soil might change its thermal properties, because salts would be having a different thermal property as compared to the minerals of the soils. All right. So, when you are talking about the soil minerals, their conductivity normally is higher than the conductivity of the salts which are going to be present in the soil mass. So, now I think you can realize the matrix is becoming more and more complicated. So, the best way is go to the site, collect the samples, do a complete comprehensive analysis of the soils, try to understand how much minerals are inorganic minerals and what is the fraction of the salts which is present in what form, and then make a model which will what is known as mixing model. Okay. Now, mixing models are going to give you an idea about what are the phases of the materials which are present in the soils and how they are influencing its thermal properties. This is what is again a multi-phase geomechanics is. So, a lot can be deciphered from the response of the geomaterial if you impose it to a thermal flux. Got it? That means, if you expose a material, a soil mass or rock mass to a thermal loading, the way this heat migrates into the material, if you can trace it out, you can characterize it better. So, in simple words, what I am saying is, if I take a soil mass and if I expose it to a thermal flux of Q, heat which is going in or which is going out, if I withdraw the heat from the soil mass, it becomes cooling. Is this correct? So, negative flux is cooling and positive flux is heating. You can torture the soil sample or the rock sample or the geomaterial sample by applying cycles of heating and cooling to see what it is really, where it is going to be useful. In most of the industrial processes where the heat flux is varying with time or the cooling is taking with time, nature itself is a good example of heating and cooling cycles. Your cycles of the weather are nothing but cooling, heating, freezing, thawing, thawing, freezing. Now, how soils or the geomaterials maintain their integrity because of these environmental changes, that is what actually we are trying to understand. So, this simulation has to be done in the laboratory. Unfortunately, all these properties are heavily dependent upon the type of method which you are using. There are several methods which you have to apply, and the question is which parameter to be accepted based on what type of determination scheme. So, this is where actually you have to use your intellect. But still, if I get a range of or a spectrum of parameters, I can always select from there, and I can say this is the parameter which I wanted to use. So, what we do in laboratory or in the field experiments is we expose the soil sample to a certain flux and then measure how much is going to come out and how the temperature is varying over a function of time and radial distance. Now, this is how the flux is moving in the medium, both heating as well as cooling. Because of cooling, how temperature is building up at a given time, at a given distance, and how the same thing is happening because of the heating process. This is what is known as thermal regime. So, most of the oil companies and most of the situations where you want to protect your facilities from the environmental changes are to be designed keeping in view the thermal regime setting in. So, what you have to do? You have to provide some thermal barriers which will not influence the subsurface constructions. You have to cut them off from the environmental changes, and remember there is a water table also. So, water table is also a reflection of the environmental change. Now, how are you going to isolate your structures from the effect of the environment which is getting influenced in the form of the water table is a wonderful problem to solve. I hope now you are realizing what is the role of consultants. So, what do? They try to simulate these type of situations and come out with an answer and provide this answer to their clients. What is the shift in the geotechnical engineering? I hope you are realizing that these concepts which we have discussed are a major shift from the conventional practice of geotechnical engineering, where we only talked about the mechanical stresses, strains in terms of bearing capacity and consolidation settlements, to all the effects now which are getting induced because of heat. This is a major shift. And as we discussed some time back, most of the situations which we have listed are going to be useful for the present day industrial practices. All right. In short, if you can measure all these properties, you have done complete understanding of the geomaterial. So, we have been now talking about determination of the properties, and by using these properties I can create a classification scheme. Hope you can realize that this classification scheme is going to be much more precise than all the classification systems and the schemes which you have used to characterize the geomaterials. Why? That was having lot of errors. Granular material, you assume them perfect spheres, clear, and then obtain their diameter by using Stokes' law. You know the limitation of Stokes' law. Sieving cannot be a very scientific way of characterizing the materials. Okay. Yes, chemical analysis gave you some near perfect answers for characterization, but the moment you talk about a flux entering into a system, it becomes much more precise. Depends again how precisely you can measure the heat which is going inside the soil mass or the geomaterial, and how much it comes out, and what type of temperature regime sets in. So, this is the whole crux of the story. Now, I will show you the type of developmental work which we did and which is now has been customized by some of the companies, and they are selling tools which are available in the market to make your job simple and easy. So, to begin with, this is a typical example of how transient method of heat has been utilized to characterize the geomaterials. This is the probe which is shown over here on the top, and this is a hollow copper tube in which we have used a So, this is the hollow copper tube of approximately 6 millimeter diameter, in which we have inserted a thermocouple which will measure the temperature, and then we have inserted a nichrome wire. Nichrome wire heats the tube. This tube can be fitted inside the geomaterial, and then this thermocouple is at the interface of the geomaterial and the copper tube. So, this gives you the temperature at the interface. This is the typical thermocouple which is normally used for measuring the temperatures at different points in the geomaterial. So, these are commercially available. This was our design based on which we created, to my knowledge, the first thermal probe which was used by my students and by the consulting world for obtaining the thermal properties of the geomaterial. This is how they look like. This is a small thermal probe which we created, a big thermal probe which we created. These are the thermocouples which we used. Then we moved on to create a field thermal probe which is approximately 1 meter long, and what we have done is we have embedded 3 thermocouples at equal distance. The whole idea was that we should get a better picture or average temperature change in the medium when we heat the probes. So, this is what is known as a field thermal probe, and you can record the temperatures at different lengths with time, and you can do the analysis to get how the properties are going to change. We also created a device to standardize these probes. So, this is a CBR mold or a compaction mold in which we used a dummy rod. So, you pack the soil mass, use the dummy rod to create a small hole, and which is slightly smaller than the diameter of the probe. Insert the probe into that, and then you can do the experiments. This is the field thermal probe which we created, and then we calibrated it using a 1 meter long steel casing. The principle remains same, and then we also created one thermodet which is for measuring the thermal properties of the powders and the soil mass which is used in the most of the cosmetics industry or toiletries which you are making, or different types of chemical units which are going to create. So, these are all creations of my ex students who educated me in this subject, and I am very much thankful to them. We also created a software where if you input the basic properties of the soils, you can get their 3 properties: resistivity, diffusivity and specific heat for a given state of compaction and the moisture content. The question is that what is transient method? The transient method is basically defined as a linear heat source. So, what you are observing here is a soil sample. This is the thermal probe which acts as a line source of heat, and then you are seeing several thermocouples which are embedded in a top lid. Why? Because as I said over here, you are finding out the temperature in the medium as a function of time and radial distance, and this gives you a response spectra of what is the thermal regime in the soil mass or the rock mass. So, little bit of mathematics which is associated with this. You must have come across this equation, differential equation. Rate of change of heat is a function of rate of diffusivity. So, alpha becomes your thermal diffusion, and then this is the radial diffusion in one direction. In toto, this is a 3-dimensional phenomena, how temperature changes with respect to time, and then you can apply some boundary conditions to solve this equation, and then ultimately what you get is a response like this. This is what is known as thermal response of a geomaterial. This is how it is plotted: temperature versus time. on log scale and on a normal scale. And this is the ultimate form of the equation which I showed you. Change in temperature is a function of time, Q is your I square R, the heat which is getting emitted, and K is the thermal conductivity. So, by using these simple devices, you must have realized that we can answer all these complicated questions which the world has been asking. Okay. S is the slope of the line. So, if you plot temperature versus time on a log scale, in the transient method or steady state method, whatever the slope of this curve is, this is what is known as S. You multiply it by Q upon 4 pi and this gives you straight away the RT value. Another interesting fact is, if you extend it on the x axis, wherever it intercepts the x axis, this is where the temperature is going to be 0. And if temperature is going to be 0, this point gives you the alpha value, diffusivity. All right. So, you have got two parameters now, RT and alpha. Density is known, you can get Cp. So, this was a simple way of finding out thermal properties of the geomaterials, which we have been using since long in our laboratory. Looking at these curves, you can also understand what type of material you are working on. So, clays will have a very high resistivity value. So, when resistivity is going to be high, this curve will be having a steeper slope. Okay. And then you can select the material for a specific purpose. Depends upon whether you want to create a thermal insulator or whether you want to create a thermal barrier. Why I am telling you this? Because there might be a situation where I do not want any heat which is getting generated inside the system to go out in the environment. So, this is where I want a thermal barrier. This thermal barrier may also act as a thermal barrier for the environmental heat to ingress inside. So, it depends upon what type of modeling you are going to do. Okay. What you have to understand is how the heating is taking place and what type of temperatures are getting created in the geomaterials because of this heat flux which is migrating through it. We moved on to determining the thermal properties of the powders, and this concept was very well utilized by the industries which are agro industries, particularly those who produce different types of grains, because when you store them in a warehouse, the thermal properties of the grains is also becoming very important. That means they should get properly aerated. If they do not get aerated, then again the heat will increase and the decomposition will start. So, with these ideas we started creating a container which is instrumented by using a thermal probe which I have shown you. This container is filled up with the powders. It could be an admixture also for that matter. It could be a cement also. It could be a powder of a rock, whatever. And then I can see how this material behaves under heating and cooling. So, what we do is by packing the powder here and then inserting this thermal probe, this whole assembly is kept in a freezer or in a heater, oven, depends upon what type of experiment you want to do. So, this is where the temperature versus time graph looks like. Again, this is a fundamental characteristic of a geomaterial. That means, if you keep that assembly in a oven, the initial temperature is very high and then let it cool down. So, I want to see how cooling response would be. You can reverse the process and you can see how the heating response would be. So, you will get thermal properties both in the heating and cooling stages of the materials. Some graphical aids can be utilized. I am sure you must have seen this type of graph somewhere else also. If you can recognize it very easily, alpha equal to d square T upon T50, consolidation theory. So, the same graph is normally used in consolidation also in getting the time factor. This is going to be Cv into T multiplied by H square is the time factor in case of consolidation theory, correct. Here alpha is the diffusivity, thermal diffusivity. The Cv term defines diffusivity of the pore pressures or the water. So, truly speaking, the physics remains same. What you are trying to obtain is d is the diameter of the soil sample, T 50 is the time which is required to attain 50% of the cooling or heating, and corresponding to that you can get the time factor directly. So, the basic physics concept remain same. The results which we get, I will spend some time to analyze and give you an idea about how these results can be utilized. So, what different types of soils, if you derive RT and plot them with respect to gamma d, what you will notice is as the density increases, the resistivity decreases, which is understood. More the packing density, lesser the resistivity. Depending upon what type of soil you are using, whether it is clay, sand, fly ash, admixtures and all, you will get different types of characteristic curves. So, what is changing here is the slope of the curves, and the slope of the curve is a peculiar value for a material. That is it. What water does? When you add water to these type of soils, what happens? As the moisture content increases, the resistivity decreases. This is what actually we discussed, because all the pores are now filled up with water, and water is having the least thermal resistance as compared to the air. So, ultimately the entire characteristic converge to the thermal resistivity of water. So, saturated soils will show you the minimum possible resistivity as compared to the driest state of the soil. So, when you talk about the material characterization, these type of nomograms become very handy. This is inverse form of the analysis would be, if I know resistivity, if I know the type of material I am going to work with, I can find out its moisture content. So, one of the ways to obtain the moisture content could be, if you know its thermal resistivity and if you know the packing density, you can find out the moisture content. Now, where this concept is used? This concept is used for establishing the compaction state of the soil mass. So far you have studied compaction states by using nuclear gauges, nuclear density gauges, by using core cutter method, sand replacement method and so on. Now you are also getting exposed to a simple situation where I can heat the soil mass, I can get its RT value, and corresponding to a given RT value, if I know the packing density and the type of the soil, I can obtain its moisture content. So, this is the method which has been used by us in creating SWCC of the soils, soil water characteristic curve. That means, if you pass heat through the soil mass and if you want to measure what is the moisture content at a given time, okay, the best idea would be keep on measuring thermal property, ascribe it to the moisture content, and that moisture content can be utilized to create SWCC. Slightly complicated thing, but if you read more and more about this, I think you will relish what I am saying better, particularly those of you who are into the consulting field, because the applications are tremendous. And I am sure many of you might be getting these problems of designing the different types of thermally activated geotechnical systems, including thermal piles and underground space. Little bit more on how the diffusivity remains constant with dry density. What happens to it when moisture content changes, these are all signature curves. So, as far as the diffusivity is concerned, it does not depend upon the compaction density for different types of soils. However, the diffusivity is a very strongly dependent parameter on the moisture content, which is what is observed over here. Then the question is, what about the specific heat, whether it remains constant with dry density or not. So, it is understood that dry density will not have much impact on the specific heat, because specific heat is a fundamental property of the material which is guided by its mineralogy, because each mineral has a specific heat carrying capacity. Okay? So, when you are designing synthetic minerals, then this concept might be very, very useful. Sometimes you will also like to understand how specific heat would depend with respect to water. This is another way of finding out the moisture content. In geotechnical engineering, most of the discussion is on obtaining the moisture content and the dry density, because this is what we wanted to know. So, if you have a device by which I can heat the soil mass and I can obtain its RT and Cp, I can compute its moisture content. This is a reverse way of doing the things. Imagine designing a sensor which can measure heat flux and temperature. So, what I have discussed over here can be instrumented. I can measure Q by putting a heat flux sensor. I can put a heat flux sensor over here, and I can measure the temperature also. So, this instrumentation can be done very easily. Now, once you have measurement of Q and theta, which most of the scientists do, I can insert a series of thermocouples here and series of heat flux sensors to know how much heat is migrating layer by layer and what is the temperature for each layer, and then I can do mathematical manipulations to obtain moisture content, gamma d, hydraulic conductivity, and so on, including the microstructure. So, this became a very powerful tool to study the microstructure of the soils, all right, which is gaining lot of interest of the guys who are working in the field of energy storage. I hope you can realize that when you are injecting carbon dioxide or any gas in the geomaterials, what is going to change is the state of moisture content, the state of saturation. Got it? Now, here the saturation is going to be two facet. One is saturation of the moisture and another one is the saturation of the pore fluid, where a gas is becoming a part of the pore fluid. This is where most of the debate is going on. How much CO2 can be stored in a porous media? How will you estimate it? How will you determine it all nine? Okay? So, that means if I can do something of this sort, I can compute the quantity of CO2 which has been injected into the porous media. Very futuristic thoughts. Somebody has to work on these topics, these ideas, to show that how things are happening. Okay, I will cut short my discussion now, and I will like to show you some interesting things which we did on a centrifuge. So, this type of modeling was done long back by one of my students, Dr. Krishnaiah, and of course, a series of master's students who came out with these scaling factors for the heat migration through the geomaterials. Now, these concepts are basically useful in designing the theories and the concepts for material characterization under elevated stresses. Fortunately, we have a centrifuge, geotechnical centrifuge in our institute. Those of you who have not seen it, you are most welcome to come and visit it. Very unique facility, where you can simulate the effect of mechanical stresses on the sample, and then you can see how heat migration takes place. So, most of the answers like thermal conductivity, thermal diffusivity, specific heat and heat flux, how it gets modeled in accelerated environment, this is what my students attempted to answer. And we created this type of a facility in the spinning centrifuge, where you can measure the heat properties. Rather than explaining to you the entire setup over here, which is a very simple idea, what I will do is I will show you the real picture, how it looks like. This is how it looks like. So, this is a soil sample which I showed you earlier. This is a data logger. This is the bucket of the centrifuge. One side you can keep the sample, another side you can keep the counter load of the batteries. And then what you are seeing over here is the switch which we created. So, when the sample is in flight, what is going to happen? This switch is going to get connected or touch the body of the bucket through which the transmission of current takes place. So, these batteries are supplying power to the thermal probe. Once this thermal probe gets heated up, the thermal regime can be established by keeping several thermocouples inside the soil mass. And then over a period of time and distance r and z, you can measure the heat temperature. So, what we have done is we have devised a simple technique by which you can measure the temperatures as a function of time, comma r, comma z for a given soil mass. So, this is how a lot of innovation can be done. Just to show you quickly the results which we obtained from these tests. These are the signatures of a material, how temperature builds up, how heat migration occurs through the soil mass. So, this is a thermal probe and these are the thermocouples. When you heat the soil mass, we want to understand how radially the heat is migrating. That means, you have to measure temperature as a function of time, and in another case you have to measure temperature as a function of radial distance. So, if you do these two things, what n indicates over here is what is the centrifugation level. N equal to 1 means simple 1 g, 50 means 50 times the gravitational force, 100 times 125 g. So, we just wanted to see how modeling of models can be done. That means, if I expose the sample to different accelerated environment, because this acceleration ultimately results into the type of gravity pulls or the stresses which are going to get created in the sample is what being studied over here. So, this is 50 times g, 100 times g, 125 times g. We are simulating the effect of stress which is coming on the sample because of centrifugation, and then we wanted to establish how heat migration occurs. So, you will notice that once you have this raw data and if you process it, you will see most of the results superimpose over each other. This is a trick or technique which is used to show that modeling of models is valid. It does not depend upon what type of stresses you are exposing to the sample. The heat migration being a diffusive phenomena, okay, it does not depend upon the type of stresses which are getting induced, clear, and these stresses are due to centrifugation, the external forces. Similarly, modeling of models can also be done for different types of radial distances. That means, how temperature is changing as a function of radial distance. So, in short, what we have done is we have exposed this sample to elevated acceleration by centrifugation, and then we are showing whether q and theta in the geomaterial remains constant or not. Okay. So, this is what the state of the art is. Now, consultants mostly talk about validation with the numerical modeling. So, to answer this question, what we did is we used FEM software ANSYS to show that whether this type of situation would yield the similar results or not. So, this is the assembly of the soil sample, top view. What we have done is at 4 quadrants we have embedded several electrodes, and this is the thermal probe at the center. So, we are heating the sample from the centrally, and then we are measuring the temperatures by using different thermocouples at different distances and time. And then these are the results. So, as expected, at the point of heating the temperature is maximum, and at the extreme end this is the ambient temperature 27.8. Now, how heat is getting distributed in the porous media or the geomaterial or the sample, this is what is being simulated over here. The way we did modeling of models there in the experimentation, now you can superimpose all the results and see how temperature changes with respect to time and with respect to distance. And this is what we showed, that both numerical results match with the experimentation results. So, in short, what I have done is, in this whole discussion I have tried to show you what is the importance of the thermal properties of the soils and geomaterials, how do you measure them, what type of simple instrumentation was developed. If you buy these instruments from market, they are very expensive, and how these results can be interpreted and how these results can be utilized in the practice. I will stop my discussion here today, and hope you must have realized that I have tried to make this very intricate topics so simple looking, which is not a fact. You have to spend enough time to master this, but that should not be a deterrent in your growth. A lot of publications are there, a lot of books have been written by people, a lot of case studies have been done. Go through all of them. What I have tried to do is, I have tried to give you the basic concepts as quickly as I could, which might help you in picking up this subject in future. All the best. Thank you.